talking is on the bottom and I can't see anything else.
Gotcha.
Oh no.
I can't see myself.
Yeah, I end up collapsing the panel that has our like video feeds because it's just you guys. You know what I look like. It's fun.
I might just like log in like on my computer and like.
Well, yeah, do that. We'll wait for you.
Yeah, we want to do.
I don't know if it's gonna like hold too much of my Wi-Fi.
Gotcha.
We'll see.
Yeah, it looks like you're up here twice, so.
Yeah.
That'll be interesting.
We'll see. But I can see the screen better.
Okay. Gotcha.
I might just, I don't know. We'll see. If I start to get like really, really staticky, let me know and I'll just cancel one of them.
Okay.
All right, you ready?
Yep. Ready as we will be.
Okay. So we're doing these systems now. So instead of just solving one equation, two differential equations at the same time.
Gotcha.
So here's our system. And it says to solve by eliminating the x and solve for the remaining differential equations. So let me copy them over here. So the way to do this, and without getting like too into detail, since you both haven't watched the videos, is that you want to rewrite your equations as an algebraic operator. I know that sounds crazy, but it's very simple. So my first equation here, the only x that I have in the equation is this derivative, and there's a 3 out in front. So I'm going to write it as 3 times the derivative of x, like that, plus 12, and then times the y, like that. So anytime you see a capital D, it just says to take the derivative of the thing that it's operating on.
So that's why we couldn't use it in math labs.
Yeah, yeah, exactly. Same thing here. So we have the derivative of x, so we're going to do d acting on x minus derivative of y, d acting on y. Now what you want to do is you want to solve this as if it was just an algebraic system. And one way of doing that is by eliminating. With this question, it wants you to eliminate the x. So to eliminate the x, we would add these two equations after we multiply the bottom equation by -3. All right, so if we multiply the bottom equation by -3, just to copy my two equations down, this is going to be a -3 dx, and then I guess technically this would be +3 dy. Add the equations. So just add straight down. The 3 dx and the -3 dx cancel out, and you're just going to be adding the y terms together. But when you add the y terms together, 12 and a 3d they're not like terms, so you just have to leave them as is. 12 plus 3d acting on y. All right, then you want to undo the operator thing. So this just distributes. You're going to have 12 acting on the y, which is just 12y, plus 3d acting on the y, which is going to be 3 and then the first derivative of y. And then you just solve this however you feel comfortable solving it. So if we get the y prime by itself, it's subtracting the 12y over and dividing by 3, we get -4y. There's a lot of different ways to solve this, but probably the easiest way would just be separable differential equations. So thinking of the left-hand side as, not that. Dy dt is equal to -4y. Then we would divide that -4y over to the left-hand side. Leave the dy there. There's still a 1 on the right-hand side, and then multiply the dt over to the other side. So this is stuff we did back in chapter 1, I think, or chapter 2.
A long time ago.
A long time ago. Anti-differentiate the left-hand side, or integrate it, I guess. So negative 1/4 just comes out, and then 1 over y goes to natural log y. Anti-differentiating the right-hand side, we're going to get a t and then a plus c. Multiply the negative 4 over there. We can just absorb that negative 4 into the constant.
Right.
And then you want to raise both sides to the, as an exponent of e. So we're just going to get y on the right, and then e to the negative 4t, and then plus c up top. Oops, sorry. But remember, when you do that, you can separate that out like this. Right, so e to the negative 4t plus c, I could use the product rule for exponents and rewrite that as e to the negative 4t and then e to the c. But e to the c is just its own constant, so we just absorb it again. All right, and then just coming back down to our answers, we've now solved for y in our system. In this system, the function y has to be this, some constant and then e to the negative 4t. Okay, so second part, now find x of t. So the x of t and the solution y found in the previous step are general solutions to the system up top. There's a couple different ways of finding x. You could start back over, but instead of eliminating the x's like we did, you could multiply by something and then add the equations together to eliminate the y's and then solve for the x. So just the same process, but the other way around. Or what you could do is that if you can somehow solve for the x as a function of y, then you can solve for that. So there's a couple different ways to do it. So what I mean by that is that we can just take this equation and subtract the 12y over. All right, so everything I just said, what we're going to do is we're going to solve that first equation for x. I guess technically x prime. So we're going to get the x prime on one side, and then we're subtracting, so the equation's over here, we're subtracting the 12y and then dividing by 3, so we're going to get negative 4y. But we already know what y is equal to because we've already solved for it. So we can just plug y into this and get x prime is equal to negative 4c e to the negative 4t. You do have to be careful at this point. You cannot absorb constants anymore because the c in this equation has to match the c in this equation. All right, the last step is that we're just trying to figure out what x is. So if this is the derivative of x, then we just anti-differentiate to get x itself. So if I take the antiderivative of this with respect to t, I'm going to divide by a negative 4, which is going to cancel out with the 4 that was already there, and we're going to get this. All right, so what we found, right, is that y was a constant e to the negative 4t. X is a constant e to the negative 4t. And when the two equations come out to be the exact same thing, I think that's when the system is degenerate.
Okay.
Let me double check. Oh, no, it's not. All right, sorry. Let me just type it in then. Didn't like that either.
So it has a C2 on the y equals. Do we need to have some kind of subscript on our C down here?
You might be right. Because it should be the same constant. Oh, I just forgot. Oh, so because we did the antiderivative here,
That's right.
I forgot to add a constant on the end of it. Oops.
So it's C1 plus C2 e to the negative 14.
Yeah. All right, but that's the process. So when you have your system, first thing that you want to do is you want to rewrite it with those differential operators. Solve it algebraically by eliminating either the x or the y, and then you're just going to have a differential equation in terms of the others. That is where you're going to have to go back to chapters 1, 2, 3, or 4 and solve that differential equation however you feel comfortable solving it. And then once you have one of the functions solved for, go back, just like we do in algebra, solve for the other one, and plug in what you know to get the remaining one. And don't forget to add constants when you end to differentiate. Cool. Is that all right? Is there any questions about that one?
It seems pretty straightforward. I think just, obviously more examples will help us get the hang of it a little bit better.
Well, let's try the next one then.
All right.
Let me copy them over. All right, so same thing. We're given the system. They want us to eliminate x and solve the remaining differential equation for y. So the same thing that we did before. All right, this one's going to be a little bit more complicated because we have a little bit more to these equations, but it's still the same process. First thing that you need to do is you need to change this into those differential operators. And it's a lot easier to do that once you have your equation in what's called written in standard form. Standard form looks like this. So you're going to have some operator on x plus some operator on y is equal to just whatever's on the other side that has no x's or y's in it. So just some function of t. For this example, it's going to be 0 because there's no terms that have a t in it. Then your other equation is going to be the same thing. So you're going to have an operator on x, an operator on y, and then that's going to be equal to something with t's in it again. We'll just call it f2. All right.
On the tests, are you going to tell us which variable to eliminate and which one to solve for?
I doubt it. No.
Okay.
Usually I would just have you to give me the two solutions, x and y.
Okay.
And you can do it in whatever order you want to, because it doesn't matter.
Okay.
All right, so to rewrite these, I'm going to combine everything that has an x in it together, everything that has a y in it, and then move all the stuff that does not have an x or y over to the right-hand side. So this first equation I'm going to rewrite as the x prime. I'm going to subtract the 6x over to beyond that, and I'm going to add the y over is equal to 0. Same thing with the other one. So for this other one, I'm going to add the 9x over to get all the x's together. Plus, we're going to have a y prime, and then we're going to have a 6y, negative 6y, is equal to 0. Okay, now we could use that differential operator. So for this first equation, just looking at the x's, I'm going to have a derivative of x, so that's going to be a d. And then factoring that x out, we're going to have a minus 6, and it's going to be that operator acting on x. D minus 6 acting on x is the same thing as these first two terms together. Does that make sense? Like you're distributing it into there.
I think that makes sense, yeah.
Okay. And then we're going to add on to this.
I'm trying to think about it that way.
It is a lot different, yeah. We only have a constant in front of the y, just the 1, so it's going to be the operator of 1 acting on the y. All right, for the second equation, we have a 9 acting on the x, plus we have the derivative of y minus 6 acting on the y. Okay. So is this step all right, going from your system to the operator way of writing it out?
It's making sense.
Okay. All right, so now is where we want to do the eliminating thing. to eliminate the x, we have to add these two equations together to make the x's cancel. This first equation needs a 9 on there, so I'm going to multiply equation 1 by 9. The second equation would need the d minus 6, so I'm going to multiply the second equation, multiply equation 2 by that d minus 6. All right, so we'll actually write that out. Multiplying the top equation by 9 is just going to throw a 9 out in front. Multiply 1 by 9, multiply 0 by 9. Multiplying the second equation by d minus 6, we're going to have the 9 that's already there, the d minus 6 that we're multiplying on as an operator, plus I already had one d minus 6 on the y, but I'm going to multiply on another d minus 6 on the y. You can, yes. So, in fact, that's what we're going to have to do. So instead of thinking about it like that, we can think about it as the 9d minus 6 acting on the x, plus we can think of this as, you can think of it two ways. You can think about it as d minus 6 all squared acting on y. Another thing that you could do, which we're going to have to do here in a second, is FOIL this out and write it as d squared minus 12d plus 36, just multiplying it out like you would if it was a binomial. Okay. Now the x terms are the same, though, right? They're both the 9d minus 6's. So this time we have to subtract the two equations. The first equation minus the second equation makes the x's cancel out because they're the same thing. The first equation has a 9 as an operator on the y, minus the operator on the second equation, d minus 6 all squared. That operating on y. Still equals to 0, though, because there's still 0 minus 0 on the right-hand side. Now what you would want to do is do the algebra here to multiply all this out and combine all the like terms together. I hope I don't mess that up, and I'm going to try and do it all in my head. All right, I don't know. I think that's right. Somebody that has a pencil and paper in front of them.
Okay.
Multiply all that stuff out.
So we FOIL out the d minus 6 squared. So that gives us d squared minus. Let me write this out on the way. So d squared minus 12d plus 36. And then that is negative. So then that would be negative d squared plus 12d minus 36.
Okay. And then combine the 9 in.
Yep. Yep, that looks good to me.
Okay, cool. So now what we want to do is we want to get out of this operator format. So we're basically just going to distribute it into there. So we're going to have a negative and then the second derivative of y. Plus the 12d acting on y is going to be 12, and then the first derivative of y. And then we're going to have negative 27 acting on the y. So negative 27y. All right, so is this okay, moving from this line to this line?
I think so. The way that makes sense to me to think about it is sort of like with the auxiliary equation, the way we kind of reinterpreted the r's.
Yeah.
It's kind of that in reverse.
Yeah, that's a good way to think about it. Okay, but now we're here. We only have y's. We need to solve this. And we've looked at doing this a lot. This is a homogeneous second-order differential equation. So to solve it, we're going to do auxiliary stuff. So we get negative r squared plus 12r minus 27 is equal to 0. I don't know if that can be factored. Probably if you multiply everything by a negative. That was funny. So can this be factored? Yeah, minus 9 and minus 3?
Yeah, 9 right?
Yeah, that's good.
I think so, yeah.
Okay, so we get two different roots here. R is going to be positive 3 and positive 9. And whenever you have two different positive real roots, they don't have to be positive. Whenever you have two real roots, that means that your solution is just going to be C1 e to the 3t plus C2 e to the 9t. And then that should match one of these over here somewhere. Yeah, this one.
Yay, we did it.
First try. All right, and then it wants to do the same thing to solve for that x. So, again, two different ways to do it. You could start back over, but instead of eliminating the x's, multiply by something that would eliminate the y's. If you like doing it that way, it's perfectly fine. Another way to do it is that we've now solved for the y. If we can find one of our equations to get just a single x on one side and then nothing but y's on the other, we can just plug it in. So now I'm looking at equation 2. So with equation 2, we're going to solve that for x. So just copying it down, solving it for x. We're there, right?
Yep, looks good to me.
We already know what the y is equal to because we found it up here. So we can just plug y into the y of the equation. Since we know y, we can take its derivative and plug that into the derivative as well. This does mean that we have to actually find y prime. So just taking the derivative of that, they're exponentials. Again, do not absorb constants at this point because these need to be the same constants in both the x and the y equations. All right, but now we can plug in. So we're going to get x is equal to 2/3 times what y was up top, c1 e to the 3t plus c2 e to the 9t. That's going to be minus 1/9 times the derivative. All right, and then you can multiply that out and combine like terms together. Hopefully. So just trying to do it again in my head a little. We're going to have a 2/3 c1 e to the 3t. This is going to end up being a negative 1/3 c1 e to the 3t. Those will add together just to be a 1/3. For the 9t's, I have a 2/3 c2, and then it's going to be a negative 1 c2. So negative 1/3 c2 e to the 9t. All right, and then that goes here. Make sure I write it the right way though. C1 e to the 3t. Great.
last step, you just combined your like terms with your C1s.
Yeah, so distributed the 2/3, distributed the -1/9. Then we're going to have two terms that have a C1 e to the 3t. So yeah, just combine the like terms together.
Okay, cool. Just want to make sure.
This term with this term combined with that term.
Cool.
I caught some of the chat, but I missed the rest of it. I caught the part where it said it wasn't mandatory, and then Hayden left like right away.
Yeah.
He was saying that he was apologizing, saying that he didn't realize classes were online, and that he was sorry about missing.
Oh, okay.
So he was freaking out that he missed class.
Gotcha.
And then when I told him it was
it wasn't class.
he dipped.
That's all right.
He was gone.
That was funny.
But welcome, Robert. Welcome, Valerie. All we were doing was just working through the first couple of examples of the 5.2 homework.
By the way, your
I
audio,
have watched the lecture, so don't worry about that. we're all kind of just doing what we're doing.
the audio on the first lecture was absolutely horrible.
Yeah,
Yeah.
I heard.
And then you decided to go ... Here's the answer.
We were so mad about that. I heard it and I was like, no, he did not just ...
I was like, I'm not even going to be bothered trying to watch the rest of these. I'm going to read the book.
Well, on the other videos, the voice sounds a lot better. I think it's just the first video where it sounds really bad because I was using a different headset and a different program.
Gotcha.
The other videos are not as quiet.
Well, as I wear high definition headphones, and you have no idea how bad it sounded in high definition.
Oh, really? I'm hoping it'll be better. I can go back for that first video and try and make it a little bit louder. I don't know if I want to I guess I'll just go ahead and redo it in the other program.
And without the ... please.
And okay, no more ...
Yeah, Riley and I talked about your ... during the video, and she laughed so hard.
Yeah, they're pretty infamous.
Oh, by the way, Riley says hi.
Say hi.
She told me next time we were in class to say hi to everybody.
Okay.
She's enjoying Japan.
She's in
I've
Japan?
been keeping up with her some on Facebook, yeah.
I know she just had a kid. I didn't know she was moving to Japan, though.
I miss her so much.
She's been in Japan for about 7 months now.
Okay.
Has it really been long? My goodness. Yeah, well, she left in October, I want to say.
Yeah.
Has that, I guess that has, oh my gosh, that has been 7 months. Good lord.
Or do we want to see another one of these?
5.
Or we can look and see, because I feel like they'll probably, change types, maybe. One of the last ones.
Number 3 looks bad.
3 looks bad.
Or 5.
Robert, you want to do 5?
It doesn't matter.
Yeah, that spits out trick stuff.
Oh, yeah, 5.
Okay, we'll do 5.
I think it's just, the format of our homogeneous stuff, but still.
Yeah, I'm surprised. Oh, this one's not. This one's got an e to the -4t on it. Number 6. And it's got initial conditions. Oh, man. All right, we'll do 5 and then we'll do 6.
Okay.
We'll do 5 real quick. Let me copy it down. All right, so same thing, right? We want to move the x's and the y's all to one side and then, write them beside each other. So for this first equation, we have the x prime, and I'm going to subtract the 2x, be close to that. I'm also going to go ahead and add the 5y over there as well. Second equation, the same thing. We're going to subtract the negative 5x over so that the x's can be out in front. And then we're going to have a y prime, and then I'm going to subtract that negative 2y and have those beside each other. The reason we're doing that is we want to think about this as an algebraic system and not a differential equation system. So we're going to rewrite the x and the y's as operators. For the first equation, I have x prime minus 2x. As an operator, that's going to be a d minus 2. The derivative of x, and then a minus 2x. The only thing that we have acting on the y is just that 5, so we're going to think of it as the operator 5 acting on y. All right, and so then the bottom equation, very similar. We have a negative 5 acting on the x, and then we have the operator derivative minus 2 acting on y. They want us to do this.
So bad to think about.
Yeah, it's not too bad. They want us to do the same thing here where we're going to eliminate the x and solve for the y. So if I wanted the x's eliminated, they have to be either the same or negatives of each other. I'm going to multiply this top equation by 5. I'll multiply equation 1 by 5. And we're going to also multiply equation 2 by that d minus 2 operator. That way we get 5d minus 2 operating on x plus 25 operating on y for the first equation. The negative 5 d minus 2 operating on x plus, this is going to be a d minus 2 squared operating on the y. And the reason we're doing this is now if I add these two equations together, the x's cancel out. So adding the two equations together, the x's are gone. I'm going to have a 25 plus the operator d minus 2 all squared. Those together operating on y. All right, no more dot, dot, dots. So we'll multiply this out. Let me scroll down some. And then combine like terms. And now we're here. The purpose of all of this was to get rid of the x's. And now we have a differential equation that only has y's. We're going to transform this back into the differential equation by just looking at the operators. D squared acting on y is the second derivative of y. Then we're going to have a negative 4. D acting on y is the first derivative, plus a 29 acting on the y is 29y. And now we're left with the same thing we had in the last example, a second order homogeneous differential equation. And to solve these, auxiliary stuff. I don't think that can be factored. No, definitely not. So we're going to have to use the quadratic formula stuff. So negative b plus and minus square root. How do you do a square root really quickly?
It might be the same as, because I know online you can do a slash and then SQRT. I think if you, I don't know if that will work.
Give me a fraction.
Try the other kind of slash.
This slash. Oh, that worked.
Hey, look at that. Cool.
Okay. So square root of would be 16 minus 4 times A times C. Somehow my square root gave up on me, but that's okay.
Maybe if you put that all in parentheses, it'll know to stick it under there.
Yeah, I think I'm going to have to do that next time.
So then
Anybody have a calculator on them?
16 minus, and it's what, 4 times 29, right? So under the square root, you get negative 100, so that's 10i. I think.
Yeah, 10i. Okay, so we're going to get 2 plus and minus 5i when you divide both of them by 2. Yeah?
Looks right to me.
Okay. And then whenever you have complex solutions for the auxiliary, that's when your homogeneous equation is going to be C1 e to the alpha t, so e to the 2t, cosine of beta t, so cosine 5t, plus C2 e to the 2t, and then sine beta t. Oop. All right, and then hopefully that'll match.
Yep, that looks like the first one, I think.
Oh, yep, excellent.
Oh.
All right, and then now we need to solve for x. So hopefully one of these two equations up here can easily solve for x in just terms of y. And again, I'm looking at the second equation. So let me copy it down. Solving this for x now, we get 5x is equal to y prime minus 2y. Dividing by 5, we get this. We already know what the y is equal to, so we just substitute y into this equation to get the x by itself. We are going to go ahead and take the derivative. I'll just do this up top this time. Oh, all right. Are you sure I can't dot, dot, dot?
Yes, please don't dot this.
I meant, yes, don't dot, dot, dot.
Okay. So we're going to have to do some product rules. The C1 e to the 2t I'll have as the first, cosine 5t the second. So it's going to be first times the derivative of the second plus the second times the derivative of the first. Okay? And then that plus the second term's product rule. First derivative of the second plus the second times the derivative of the first.
Ooh, that was my dog. Sorry about that. She needs to go out, so I think my mom might be able to come get her. I'll be right back.
Okay. I think we can combine a bunch of like terms from this. So this is going to be... Oh no, we can't combine anything, can we? Let me just write it out so it looks a little bit nicer.
Alright, I'm back. Sorry about that.
It's okay. Okay. See, I don't think anything can get combined together here because they're all different stuff. Well, we'll just leave it like that. Okay, so now plugging it in, we're going to get x is equal to 1/5 times this derivative up top. This is one good thing about working in Word. And that's going to be minus 2/5 times the function itself. I feel like I circumvented the dot dot dots.
Yeah, you kind of did.
I can't get it all on one screen, sorry. So I'll distribute the 1/5 into all of that. Distribute the negative 2/5 into the other one. Alright, looks gross. Kinda is. But hopefully we can combine some stuff together. So here we have a C1 e to the 2t sine 5t. I know what we can do. Alright, here we go. So what I'm going to do is I'm going to go ahead and factor out an e to the 2t from everything. Then I'm going to combine everything that has a sine and a cosine together. We'll do cosine first. So does that make sense what I'm going to try here? Factor out e to the 2t. Then we're going to have some stuff times cosine and then some stuff times sine added together. So everything that has a cosine, I have a 2/5 C1. That's coming from this second term. This has a cosine, so a plus C2. This has a cosine, so a negative 2/5 C1. Oh, so these just cancel out and go away, huh? I should have seen that already, sorry. So do you see that? I have a 2/5 C1 and a negative 2/5 C1. So they're going to disappear. For the sines, I have a negative C1 for the first term. I have a plus 2/5 C2, and then a negative 2/5 C2. So those are going to disappear as well. So it looks like I'm just going to have the e to the 2t, C2 cosine 5t plus, nope, minus C1 sine 5t. And that should be it. There's nothing else we can do here, so let's plug that in and see if it works. So e to the 2t times C2 cosine of 5t minus C1 sine of 5t.
You did a bracket instead of a parenthesis.
Oh, good catch. Parentheses. Yay.
Cool.
Alright, that question took way longer than I wanted it to. Sorry about that.
Wow. Well,
It was just those derivatives.
Right.
Yeah, that was a long question. I was lost, but it's okay. I'm here. I made it.
Yeah, you can always watch it from the beginning because he's recording it. So
I am, yeah. I'll put the video up right after this.
cool.
All right, I know we said we were going to do number 6, and we still can if you guys want to stay late. But up to you. We could always wait. If you're coming Thursday, we could do it on the one on Thursday. On the earlier one.
I would say maybe let's do it Thursday. That way we have a chance to watch the lecture and kind of absorb the process before we jump into one that has initial value stuff to plug in. But that's just me. I mean, if you guys want to do it,
Yeah.
I can hang out.
No, we can wait.
Yeah.
Let me ask you this. Does 6 o'clock at night work better on Thursdays? I tried to make 2 different times so that more people could hopefully come. Is 11 just too early? Do you guys have other stuff going on in the mornings?
Yeah, and I mean, I work 8 to 2 on Thursdays. So
Okay. How about everybody else? Changing it to 6 o'clock at night on Thursdays as well? Would you be able to come to that?
That's fine.
Works for me.
Yeah.
Alright, I might do that then. We'll just do 6 o'clock Tuesdays and 6 o'clock Thursdays.
I have a feeling no matter what time it is, it'll always be the same people that call.
Probably, yeah.
yeah, I think that's an accurate assessment.
Okay, cool. Well, thanks for coming tonight. Yeah, work on those homeworks. I'll reshoot that first video with better audio and no ... So then watch that and work on this first homework. And I mean, after this, hopefully you won't even need the first video because I showed you how to do pretty much everything you need to do.
Right. Okay. Sounds good. So, I guess we'll see you Thursday then.
Yeah, I'll be here 6 o'clock on Thursday.
6 o'clock on Thursday.
Yep, see everybody then.
Bye.
Bye.